All right, so let's work on problem 6 and 7 here. They're both basically the same idea where you have an equation, you have the two reactants, and you have to figure out how much of one of the products you can make. So here you have the situation of photosynthesis. You've got a plant who's got the ingredients for photosynthesis, carbon dioxide and water, and we want to find out how much glucose they make. They also make oxygen, but we really don't care about that in terms of this problem because it asks us about the mass of glucose. So what we're going to do is say we start with 8 grams of CO2. We want grams of CO2 to cancel out, so we put it down there. We want to find out the mass of glucose, so grams of C6H12O6 goes up here. Once we fill in our numbers, we're going to end up with how many grams of C6H12O6 we can make. So now all we need to do is look at our balanced equation to get the numbers that go here. So let's do the glucose first. You got carbon times 6, carbon's 12 times 6 in the formula, hydrogen's 1 times 12, and then oxygen 16 times the 6. So figure out what all that is. Comes out to 180. So that's 1 mole of glucose, and it's a 1 because there's an imaginary 1 here. But over here, carbon dioxide, if you add, forget the coefficient, if you add carbon, which is 12.0, and oxygen times 2, that's 32, 16 and 16. If you add those together, you get 44 grams. That's 1 mole, but you don't put it here because you also have to include the coefficient. 6 times 44 is 264 grams. So that's how we get that number. Remember, it's whatever 1 is, and then use your coefficient. So 8 times 180 divided by 264, and we realize that we could make 5.45 grams of glucose if we run all of our carbon dioxide and it hits 0. Now that's assuming we have enough water. So let's now focus on the water and see if we actually do have enough to make 5.45 grams. So we start with 34.0 grams of water. Notice I put a number, a unit, and a formula. I'm going to do the same thing here. Here's my unit and my formula, and we'll get the number in a minute. So grams of water. And then up on the top, we want to find out, same thing, how many grams of glucose can we make? So it's still 180 because that comes from our balanced equation. And now we're going to focus on water. Hopefully you remember by now, water weighs 18 grams. 6 times 18 is 108. So put that there, do the basic math, and you realize that if we use up all our water, we could actually produce 56.7 grams of glucose, assuming we had enough of the other reactant, which is carbon dioxide. So now we have two amounts, and the question is, which one do we pick? Well, I cannot make 56 grams, or the plant can't make 56 grams, because the moment 5.45 grams are made, all the carbon dioxide is at 0. It's gone. It's used up. It's been converted to carbon dioxide or to glucose. So this is the max. This is my theoretical yield. I can only make 5.45 grams of glucose. There's no way on earth I can get anywhere close to 56 or 57 grams because I don't have enough carbon dioxide to do that. So here's my theoretical yield. Now, this is the amount I make when this runs out, so that limits me from making more. So carbon dioxide is my limiting reactant. I have plenty of water. I have enough water to make 56 grams, but I'm only making 5. So I have plenty of water left over. That's my excess. And finally, I have a question here about percent yield. It says the plant actually produces 5.40 grams of glucose. We said that it should be able to, theoretically, if everything went perfect, produce 5.45. So we have a very efficient plant here. They're only off by a little tiny bit. And then multiply by 100. And remember, what we're looking at here is the positive way to look at this. We're looking at, here's your target. How close did you get to your target? So when you do the math here, the percent yield comes out to 99.1%. So we made 99% of what we should make. That's a very efficient plant. Remember, the opposite of this is looking at error. Error is saying how much did you screw up by? That's that AV minus EV, absolute value, divided by AV. That's not what we're doing here. What we're doing here is actual divided by theoretical. And what percentage of what you should have gotten did you get? So this is obviously extremely efficient. All right, the next one is kind of along the same line, but you just have to think a little bit down here at C. It says, iron is obtained commercially by the reaction of hematite. with carbon monoxide. So here's my two reactants, and the question focuses on grams of iron. So yeah, carbon dioxide is produced also, but this particular question doesn't really care about that. We just want to know about grams of iron. So start with the first one, 25 moles. Like moles, these are nice and easy because I can just use the coefficient. 25 moles of Fe2O3. I immediately put moles of Fe2O3 up there or down there, and then I want to find out grams of iron, so G of Fe. And I'm going to end up with how many grams of iron I can make when I react all 25 moles. Now, moles of iron oxide, I look up here. There's an imaginary 1 there, so that's nice. Put a 1. Grams of iron, I look and I see, well, 2 moles of iron are in my balanced equation. So if I was to react 1 mole of iron oxide, I would make 2 moles of iron. Now, we need to get grams, and we know based on the periodic table, 1 mole is 55.8 grams, but the balanced equation, the perfect ratio, says I need 2 of them. So 2 times 55.8 is 111.6 grams of iron. So now I take my 25 times that divided by 1, and the final answer for this is 2,790 grams. So if I use up all 25 moles of iron oxide, I can make this many grams of iron. That's assuming I have enough carbon dioxide to go with it. So now let's just focus on the carbon dioxide. This says I got 30 moles of carbon monoxide, CO. I want to say when I use up all my CO, how many grams of iron do I get? So I'm using the same numbers on top, 111.6 grams, and then moles of CO, I take this directly from my balanced equation, 3. So 30 times that divided by that is 1,106 grams. So again, I have 2 numbers here. Which one do I pick? It's always the lower. That's my theoretical yield. When my carbon monoxide runs out, I will be able to make 1,116. I can't make any more. I can't even go close to this because as soon as I hit this point, one of my reactants is gone. So carbon monoxide is my limiting in this example. I have plenty of Fe2O3, plenty. I can make all this 2,790, but I can't because I run out of carbon monoxide. Finally, it says a mining company is testing out a new method of extracting iron from the iron ore. The old method is 45% yield. Not too good. Remember, here's the target. They're only getting 45% of what they should be getting. So they're hoping to find a different method that'll be more efficient. They ran their first trial with the new method, and they produced 891. So the question is this good or is it not? Is it better than 45% yield or is it worse? If it's better, obviously, they're going to use that method. So this is their actual yield, 891, and we need something to compare it to, so we do stoichiometry, which we just did. So our theoretical yield is always from stoichiometry, from the balanced equation. So we're saying that they should be making 1,116 grams of iron. This is how much they made. This is what they should be making. Divide the 2, multiply by 100, and you get 79.8% yield. So this now exceeds the 45. Now we're up here at just about 80% yield. So this is better. So the new method is more efficient than the old one. And finally, you should be able to think about a reaction and come up with 4 reasons why the actual yield is not necessarily the same as the theoretical yield. One of the reasons that you're not getting as much as you expect to get is possibly you didn't let the reaction run long enough. So time is a problem. It didn't complete. You assumed you should get all of this, but if you only let the reaction go so far, you're not going to get all of it. So you might get less. So time, how long did the reaction take to complete, and did you give it enough time, or did you cut it short? 2, the purity. Do you have reactants there that are pure or impure? If there's some impurities in there, then it's not all reactants, and you're not going to produce as much product as you have because you have something else in there. Along those same lines, you might have some side reactions. You might have some other things going on that are not producing the product that you expect to get. And finally, you've got your product, but then you have to collect it, or you have to extract it, or you have to transfer. And maybe doing these things, your lab processes might not be as clean as somebody else's. You might be losing stuff along the way. You might be not as meticulous as somebody else. So you might be losing some more product. So all of these things keep you from getting 100% yield. Keep your actual yield from being your theoretical yield. If you should get, I don't know, 25, do you actually get 25 or do you get something lower than that? And if you got something lower, then ask yourself, why did I get it low or something lower? And then think about the reaction itself and see how these 4 ideas fit into that reaction. And be very specific. Hint, hint.